As a second topic of today, let's discuss about stress on oblique plane. Before talking about this, let me make a comment. So in reading our textbook, you can see the character P, which refers to force. Okay, so you might get confusion because most freshman physics and most high school physics book use P to refer pressure. However, please remember that P in our textbook refers to the force. Okay, so um, I think that when I was like a high school, no, not high school, freshman and sophomore in university, I felt a little bit confused about seeing new notations because different textbooks use different alphabet characters for referring different quantities. So yeah, in the beginning it might be confused because back in high school you are on the like a standardized education system, so everybody in your generation use exactly same textbook and exactly same notation in like a university entrance 수능 exam. But now as you become like a college student, as you become graduate school student, you're gonna expose it to like a new textbook and new website, and each of them gonna use different notations. So please get used to accepting the new notations. Okay, but anyway, let's move on to the our original topic, the discussion on stress on oblique plane. So for when you consider a structure under tension, and if you focus on this plane that is orthogonal to the force, you can define normal force quite easily and shear stress quite easily. Okay, like this: shear stress will be 0, normal stress will be P over A. However, if somebody asks, okay, let's take like angle theta from this perpendicular line and try to imagine this yellow oblique plane, and ask you to define normal stress and shear stress, and then you have to think about how you can do it. So first thing you have to do is you have to decompose this applied pressure P, no, applied force P into normal part and shear part. You have normal part and shear part. You have angle theta here. This is side view. Okay, now then you can see from trigonometric relationship, Pn must be P times P times cosine theta, and Ps shearing force is P times sine theta. Okay, so this is a force which is a vector quantity, and you can see that it follows the vector transformation rule. Now about the this area must be larger than the area A. This is area A, and area at this surface A theta is A over cosine theta. Now if you define sigma theta and tau theta, which is normal stress defined on here, shear stress defined on here, and you have to do Pn over A theta and Ps over A theta. Okay, then what you're gonna get is it must be P over A cos square and P over A sine theta and cos theta. Okay, now if you replace P over A as sigma of the original coordinate system, yeah, you can see this sigma theta becomes sigma multiplied by cosine square theta, and for tau theta becomes sigma multiplied by sine theta and cosine theta. And you might feel confused because back in freshman physics, when you discuss about vector quantities only, you sometimes see sine theta, sometimes see cosine theta, but you never seen cosine theta squared and sine theta cosine theta. Okay, the reason why you see this interesting angle dependence is that because stress is not vector quantity. As I told you in the lecture 1, stress is tensor quantity, and tensor follow tensor transformation law. Okay, so regarding the details about this mathematics, you're gonna get some exposure in solid mechanics 2, undergraduate solid mechanics 2 course, or you can get like even better and detailed instruction about this mathematical relationship in advanced mechanics course in graduate school. Okay, so please remember that stress do not follow vector transformation rule because stress are tensors.